This week will be devoted to two topics. One is the numerical use of Fourier series. This is this first video, first two topics. And then it's going to be the introduction to PDEs and the start towards the heat equation. So let's start with the numerical use of Fourier series. We have seen how we can analytically handle Fourier series. How can we use them in a numerical environment to approximate solutions of ODEs? Let's think about the fact that we want to find a periodic function f, and we're studying it over the interval minus L to L. We know that such a function can be rewritten as a Fourier series, either with the sine-cosine base or with the complex exponential sum. In either of the two ways, this new setup allows us to describe the full function in the full interval only by knowing discrete information. But by that I mean A0, A1, A2, so on, B1, B2, so on, or C0, C plus 1, C minus 1, C plus 2, C minus 2, C plus 3, C minus 3, and so on. So we changed a problem that is continuous to a problem that is discontinuous, in the sense that it's just computed at some integer values. So the idea of using Fourier series for finding numerical solutions is that instead of searching for f of x, we search for Cn. So we go from f of x to Cn for n in z. F prime can be replaced by I kn Cn for n in z. A times f of x is A times Cn for every value of n, and for any A complex, and so forth. So we can make any transformation that we can do in f, we can transform it in a transformation on the infinite by infinite vector of complex values associated to its Fourier series. So we went from having an ODE that I'll write it as capital F of small f equals to 0 to an algebraic problem. Here I interpret capital F as a differential operator, and we apply some sort of transformation, and we have changed the problem for trying to find a function to trying to find C. And the new problem that we have, that I'll be trying to be more precise further on, but I'm now going to be just noting it as capital F hat. Remember that hat is sometimes used as a Fourier transform. And now C is this by infinite vector. So as an example, let's look at y second derivative equals minus y. We know it's periodic on minus pi to pi. So we transform this ODE in a zero finding ODE, in a homogeneous ODE, so y second plus y equals to 0. And we transform y through the Fourier series. So the unknown y is replaced by the unknown Cn for every n. So we replace the second derivative of y by the ikn squared Cn e at the ikn x with a sum for every n integer. So we replaced y second plus y equals to 0 to this infinite by infinite sum of I kn all of it squared Cn plus Cn e at the ikn x summing over every n equals to 0. And looking at this formula, one of the things we want to remember is that the complex exponentials are linearly independent functions. So a sum of complex exponentials with different powers is equal to 0 only if every single term is equal to 0. So we shifted from having an infinite sum but only one equation to having infinitely many equations, each one being fairly simple. And this is an algebraic problem. Actually, infinitely many algebraic problems. So we can replace kn, we actually know it explicitly, is n times pi divided by L. In this case, L is equal to pi, so this simplifies. Kn is actually equal to n. So we retrieve that I kn squared Cn minus Cn is equal to 0 if either we have Cn equal to 0 or I kn squared plus 1 equals to 0. Yeah, there is a minus sign that is wrong here. So if we solve that, we have kn equals plus or minus 1. What does this mean? That either we have kn equal plus or minus 1, or we have Cn equals to 0. So we have that y can only have terms c1 and c minus 1 to be non-zero. Also remember that c minus n is equal to the complex conjugate of cn. So considering both of these elements, then we get to the conclusion that y is a linear combination of sine of x and cosine of x. That is what we would expect looking at the equation. So it does help us to go through this, or in some situations it can be very helpful. In this case, we did everything by hand, but we can ask the computer to solve it for us. So going back to the shift from ODE to algebraic problem, one problem that we have here is that the unknown that we're trying to solve is infinitely long. It's actually by infinitely long. So instead of trying to solve for every value of n when we're looking at Cn, we just try to solve for finitely many. We say we truncate C and we retrieve C hat that has zeros for indices in absolute value bigger than a certain number. In this way, we only have finitely many non-zero values, and we can use a computer to solve it. We say that C hat is a truncation of C. Now we have an algebraic problem. It's finite, so we can use a computer to solve it. So let's try to work through an example. A famous equation that always has a periodic solution is called the van der Pol equation. It's this second order homogeneous ODE. We know it has a periodic solution, so we'll try to find it. There is a parameter that is called mu, and we have to set it strictly bigger than 0. You notice that this mu is equal to 0, then we go back to the previous equation. So we try to find a periodic solution. And the first problem that we bump into is that we don't know the period of the solution itself. So we want to rescale y of x such that y of x with the rescaling is periodic on a period that we know about. So we replace y of x by y of a times x with some a real number. If we do that, then y prime is replaced by a y prime, a of x. This is a rescaling of the x-axis. It's called time rescaling, even though we haven't specified that the direction we're using is the time, just because that is most usually where it's used in physics. So now we replace our van der Pol equation with y second plus mu 1 minus y squared times y prime plus y equals to 0, and we replace y second by a squared y second computed at ax. We replace y at the power 2 by y at the power 2 computed at ax, and y prime we replace it by ay prime. We choose a such that y ax is periodic over minus pi to pi. We don't know a. That means that a has become another of the unknowns that we want to solve for. We know it exists, and that's why we can do this trick, but we don't know it yet. So we have this new equation with a's popping up in a lot of positions and y second, y squared, y prime, and y popping up as well. And we want to replace y computed at ax by a Fourier sequence. Now that a Fourier series. Now that we know that we are on the interval minus pi to pi, we know that kn is equal to n as before. But we might have the problem of like, what is y squared? Well, in general, if you have two Fourier sequences, when you make the product of them, you retrieve another Fourier series. This is true in general. We already have seen some similar situations. And you can determine the new coefficients of the new sequence, of the new series, based on the coefficients of the previous ones. There is here an explicit formula. So in the product series has coefficients dn, where dn is equal to a sum of infinitely many values for a going n minus m, and change with m changing, and b being b with the index m. We write it as d equals a convoluted b, with a convoluted b being the discrete convolution. So we take our equation, our ODE, we replace every derivative by ik, and we replace any multiplication by convolution. And we have this new bunch of things. As before, we can make a big sum of everything with respect to the basis e at the ik and x, all the sum equal to 0. As before, because the complex exponentials are linearly independent, this is solved if and only if the coefficients are 0 for every single n. Remember that we want to solve, we want to truncate the problem. So we want to say that we are not solving for all of Cn's, we're only solving for small indices. And we're replacing in the convolution also c hat instead of c, where c hat is 0 after a certain moment. So now we have a finite number of equations that we can solve, and we can just ask the computer to solve it for us. Just a brief note, we have 2 plus 1 equations given by the previous slide, but 2 plus 2 variables. Where is this extra variable coming from? Remember when we introduced the variable a to rescale the period? That is the difference. We have one equation for each Fourier coefficient that we want to solve for, but we also have one extra unknown that we want to solve for. So we need an extra equation. Why is it? Intuitively, what it means is that when a periodic function is a solution, then if you shift it, that is still a solution. So if yx is a solution, yx plus 3, for example, is again a solution. But we don't want this ambiguity when we're trying to solve for an equation. So we add an additional equation in our problem to fix for this shift. One possibility is setting the value of y at time 0. It's easy, and for the van der Pol that works, so that is what we're going to be doing. We add an equation that is y0, y at time 0 is equal to 0. And we check what it means with respect to the Fourier coefficients, and we find that it means that the sum of all the Fourier coefficients must be equal to 0. So they have to cancel out. With this new equation added to the ones in the previous slide, then we have the same number of unknowns as number of equations that we want to solve. So we can ask a computer to just solve it for us. And when we fix mu's, we can find a solution. These are numerically computed solutions for various values of mu. Well, for mu equal to 0, we have just the sine and cosine with the rescaling. And then for different values of mu, we get like slanted.